We can observe some of these properties if we look at object under a microscope. A blade, like a knife blade, will often have, it'll be made from different types of steel. Some steel is harder and more brittle, and then there's other steel that is softer and more flexible. So if somebody's making a blade, they will want to make the edge of the blade out of that hard, brittle steel, and then make the body of the blade out of the more flexible steel, so that it can flex and bend and absorb some of the impact experienced by the hard edge. And what we see here in the first picture is the division between the hard edge and the more flexible spine. On a gear, you can also harden the teeth of a gear. Uh, there are various ways to harden metal. Some involve heating it, and some involve hitting it with tools or tool hardening. So on a gear, you might make it out of soft or what's called mild steel, and then harden the teeth because you don't want the teeth to wear away. But you also don't want a crack to extend throughout the entire gear. So that when it's harder, it's more brittle. So it's okay to have the teeth be hard so they don't wear as much. But then the body, it's good to make the body out of soft steel so that it doesn't crack as easily and destroy the gear. We can look at models of these materials. So not these materials. We can look at models of materials to note the important properties. These are biological models. Now, remember, a model focuses on certain specific features of a phenomenon, or in this case, a material. So um, this is not a realistic, this is not a photorealistic drawing. This is a model that shows the structure of a protein or shows the structure of an enzyme and receptor. And these both highlight different properties because the protein model on the left shows how the protein is shaped and folded. The model on the right shows how the receptor fits into the enzyme. That's not what the enzyme or receptor really are going to look like, but that's showing that they fit together like a lock and key. Well, all right, let's just look at this. The choice of model for the protein shows that its structure has long helix shaped parts. Okay, helix is a spiral. You can predict that the protein will be flexible because it's made of those long strands, so it's likely to be flexible. In contrast, the second model shows how an enzyme and receptor fit together. They fit together like puzzle pieces or like a lock and key. You might infer that a different enzyme and receptor are likely to be shown as a different shape because different enzymes are shaped in a way that different receptors fit on them. The helix shapes of the protein model look like springs, and that suggests that the protein is flexible. These strands of protein can probably wrap around each other and become intertwined. The enzyme in the model would fit in the receptor shown, but a different enzyme and receptor might be shown as circles or triangles. As long as they have complementary shapes that fit together, then that would be suitable for an enzyme and receptor. Now, remember the phenomenon that we saw at the beginning of the unit. We had these superheated blocks. They were several thousand degrees, and then this guy just grabbed them and picked them up. So, what 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 do what have we learned? What have we learned about the structure of materials that might start to help explain how these retained so little heat, how they gave off their heat so easily? Well, if you think about it, this cube is probably not very dense. It's probably filled with a lot of air pockets or empty space. And so it's also very light. And in fact, this material is quite light. So if it has a lot of empty space in it or air in it, it would need to have an internal structure that enables it to hold its shape even with empty space. So that tells us something about what structure would be needed to create this kind of material. This is a very unusual material, but but uh, but it's important for space travel.